Imagine trying to understand a sentence by looking at each word in isolation. That's how early machine learning treated data. In this topic, we'll follow the story of how models gradually learned order, memory, and context, step by step, until we arrive at modern transformers. You've already seen what machine learning is and why sequential data is special. Now we'll walk the historical path, from traditional ML to neural networks, then to RNNs, LSTMs, and GRUs, and we'll see where each of them falls short. That perspective prepares you to appreciate why attention and transformers were needed next. Think of classical machine learning as working with neat spreadsheets. Each row is independent, and the model only sees summarized features, counts, averages, and flags. That works for things like credit scoring, but language is a flowing sequence. Meaning depends on order and on links spread far apart, like a pronoun referring back several sentences. To capture that kind of context, we need models that read step by step and remember what came before. Bag of words is like dumping a sentence into a bucket and just counting each word. We don't care about order, grammar, or context, only how many times dog, bites, or man appear. That simplicity makes it fast and effective for tasks like spam filtering. But it completely misses, meaning that depends on word order or subtle wording. TF IDF takes a smarter step beyond simple counting. It boosts words that appear often in a document, but are rare across the collection. Those weighted vectors feed classical models like logistic regression and SVMs, which already work well for tasks like spam or sentiment. But they still ignore word order and deeper context. Bag of words and TF IDF were great first steps, but they flatten language. They ignore word order, grammar, and phrases. So dog bites man looks like man bites dog. They also give the word bank the same representation in every sentence. And their huge, sparse vectors don't generalize well, pushing us toward richer, context-aware models. Neural networks change the game by learning features automatically. Instead of us defining rules like look for this word, the model discovers patterns directly from text. Word embeddings push this further. Each word becomes a vector, and similar words sit near each other. However, basic feed-forward networks still expect fixed-size inputs, so variable-length sentences need something more sophisticated. Sequential data, like text or time series, depends not just on what is present, but on the order things appear. Traditional feed-forward networks see every input as a one-shot vector, with no built-in way to remember what came before. Recurrent neural networks address this by reading data step by step and carrying a hidden state that summarizes past information. Recurrent neural networks process a sequence like a person reading a sentence, one word at a time. At each step, they mix the current input with a hidden state that acts like memory. That hidden state keeps being updated, so information from early words can influence later decisions. The final state can summarize the whole sequence for tasks like sentiment classification, while intermediate states let the model make a prediction at every time step. RNNs shine whenever you care about local word order and short-range context. They're useful for language modeling, next word prediction, or simple sequence labels, because they read tokens in order and keep a running summary. However, they're fragile with long sequences. Gradients can vanish or explode, so learning long-term patterns is hard. In practice, they remember only a short window, and training stays slow because each step depends on the previous one. LSTMs and GRUs are upgraded versions of RNNs that tackle the memory problem. They introduce gates, tiny controllers that decide what new information to store, what to forget, and what to output. LSTMs keep a separate long-term cell state, while GRUs simplify this with fewer gates. Both can capture longer dependencies and train more reliably than vanilla RNNs. LSTMs and GRUs were a huge leap over simple RNNs. They finally made it practical to capture longer-term context, which unlocked early breakthroughs in translation, speech recognition, and language modeling. Yet they still march through sequences one step at a time, struggle with very long inputs, and become slow, expensive, and hard to scale as models and datasets grow. RNNs, LSTMs, and GRUs were a big step up from bag of words, but they came with serious trade-offs. They respect sequence order and capture context, yet they process tokens one after another, so training can't fully exploit GPU parallelism. Their memory of very long sequences is still fragile and costly. Attention and transformer models were introduced to keep order and context, but with direct long-range connections and massive parallel processing. By now, we've moved from static counting to RNNs that remember in sequence to attention mechanisms that can look everywhere at once. The key shift is no more squeezing everything into one hidden state. Attention directly links any tokens that matter, enabling long-range context and paving the way for transformers. Take a breath and let this sink in. You now understand why sequence models mattered and where they hit a wall. In the next module, we'll relax those constraints and see how attention breaks that wall, leading to modern transformer architectures.